In this topic, we'll turn a generic transformer into a model tailored to your data. You'll see step by step how to fine-tune it for text classification tasks like sentiment or spam detection, and how small adjustments turn a general model into a powerful task-specific one. You've already seen why sequences matter, how transformers work, and how to run pre-trained models with Hugging Face. Now we're in the middle of the journey, taking that generic model and specializing it for a single classification job, such as sentiment or spam detection. We'll walk the full pipeline, from data and tokenization through training and evaluation. Mastering this bridge prepares you for the next step, prompting and interacting with larger language models. Think of this as using a foundation versus training a specialist. The pre-trained model has already spent huge compute learning grammar, vocabulary, and general patterns from massive text. Fine-tuning takes that broad knowledge and nudges it toward your task, using a smaller labeled dataset. We're not relearning language from scratch. We're aligning an existing expert so it predicts your labels accurately, with far less data and cost. For learning fine-tuning, we'll stick with simple binary classification problems. Think, is this review positive or negative? Or, is this message spam or not? These tasks have clear labels and plenty of public datasets with known baselines, so it's easy to tell whether your model is working. Choose a dataset small enough to train on a laptop and aim for roughly balanced classes so you're debugging the model, not fighting dataset bias. Before any training, we decide exactly what the model should predict. Labels translate human ideas like negative and positive into machine-friendly numbers such as 0 and 1. Each example is then stored as a pair, the input text and its label. Finally, we check how many examples belong to each label to spot imbalance early. To build trustworthy models, we partition data into 3 roles. Training data, usually around 70 to 80%, is what the model actually learns from. It updates the weights. Validation data, about 10 to 15%, is used for tuning hyperparameters and deciding when to stop training. Test data, another 10 to 15%, is locked away until the end for a final, unbiased check. In Hugging Face datasets, these splits often exist already, or you can create them with train test split. The datasets library is your shortcut from the Hugging Face hub to a usable dataset object. With load dataset, you name the dataset you want, like IMDb, and it downloads, caches, and sets up train, validation, and test splits for you. From there, you can inspect a single example with dataset train and check dataset train. Features to see the schema you'll feed into tokenizers and training pipelines. Transformers speak numbers, not words. Tokenization is the assembly line that takes raw text, chops it into tokens, and maps each token to an ID from the model's vocabulary. That's why we always pick the tokenizer that matches our pre-trained model. Padding and truncation then reshape every example to the same length. The tokenizer returns input IDs plus an attention mask, which tells the model which positions are real text and which are just padding. Here we're building the bridge from raw text to model-ready tensors. You define a tokenized function that takes a batch of texts, applies the tokenizer with padding and truncation, and returns the usual fields like input IDs and attention masks. Then you call dataset.map with batched equals true, so every split is processed efficiently. Finally, you set the format to PyTorch so training loops and the trainer API can consume the dataset directly. To turn a generic transformer into a classifier, we add a small prediction layer on top. With Hugging Face, AutoModel for Sequence Classification builds this for you and loads a pre-trained backbone like Distilbert. You control how many classes with num labels, and you can map IDs to readable names using ID2 label and label 2ID. Internally, the transformer produces a vector, and the classification head converts that into logits for each label. Fine-tuning behaves a lot like driving a car. Hyperparameters are your dashboard controls. Learning rate is the step size the model takes when updating weights. Batch size is how many examples it sees at once. Epochs are how many times it loops over the data. Choosing reasonable values keeps training stable and avoids wasted compute. The trainer is your high-level training engine. You bring 3 things: a configured model, a tokenized dataset, and training arguments that define hyperparameters, batch size, logging, and evaluation strategy. Trainer then handles the whole loop: batching, forward and backward passes, optimization steps, evaluation, and checkpointing. You call trainer.train, monitor loss and metrics, and stop when performance plateaus, leaving you with a fine-tuned classifier ready to use. Once your model is fine-tuned, think in terms of quality assurance, not just a single accuracy number. Run trainer.evaluate on held-out data and inspect precision, recall, and F1 to understand different error types. Then, look at a confusion matrix to see which classes get mixed up. For example, neutral being predicted as positive. Relate those mistakes to business impact, and watch for signs of overfitting. Great training scores, but weak validation performance. With training complete, put the model on text you actually care about. Use the text classification pipeline for quick experiments, or call the model directly with tokenized inputs. Try obviously positive, negative, and spammy messages, but also tricky, ambiguous ones. Compare predictions and confidence scores with your own judgment, and note patterns that suggest new training data or fine-tuning tweaks. Pause for a moment and notice how far you've come. You can now turn raw text into a fine-tuned classifier that actually works. Next, we'll zoom out and explore prompts to steer full-size language models.